Hi, my name is Lindsay Ehrlich, and this is my Lab 3 circuits report. As a brief introduction, the purpose was to predict, measure, and examine the behavior of ohmic resistors and capacitors. The system was the circuit, and the surroundings were the environment. As a results preview, we examined both the loop rule and Ohm's law using circuit 1. When examining the loop rule, we found that delta V was summed up to be 0.015 volts, which was not exactly 0 volts as we expected. When we examined Ohm's law, we found that the calculated resistance was a little bit higher than the actual resistance. In our RC circuit, we found that a higher resistance bulb equals a longer discharging time. Some fundamental principles that we use. The node rule states that the total current flowing into a node equals the total current flowing out of a node. The loop rule states that the sum of all potential differences in any closed-loop circuit equals 0. Ohm's law states that the voltage, current, and resistance are directly proportional to each other in the equation V equals IR. The capacitance basically just says that capacitors can store energy in the form of electric charge using the equation C equals Q over delta V. When examining the loop rule with circuit 1, the setup was two 1.5 volt batteries, 2 ammeters, and 2 resistors, 47 and 100 ohms. The procedure was to first predict and record current 1 and current 2 with the initial setup. Then we reversed 1 ammeter and recorded the new current. We replaced 1 ammeter with a voltmeter and then measured voltage differences across the entire circuit. And then we added all the recorded voltages to check the loop rule. Our current 1 and current 2 predicted was 0.02 amps. We used Ohm's law to predict this, where V total equals 3 volts and R total equals 147 ohms. The current 1 and current 2 actual was 0.02 amps, which is great. That means our prediction was correct. When we reversed the ammeter, the current was negative 0.02 amps, which is exactly what we expect, the same magnitude and the opposite sign. And then the voltage differences across the 47 ohm resistor was negative 0.902 volts. Across the 100 ohm resistor was negative 1.917 volts. Across battery 1 was negative 1.367 volts. And across battery 2 was positive 1.463 volts. So the sum was 0.015 volts, which is not quite the 0 volts we expect by Kirchhoff's loop rule. When we examined Ohm's law, the procedure was to put a voltmeter across a 100 ohm resistor and record the voltage and current. Then we replaced the voltmeter with an ammeter in parallel and recorded what happened to the current in the other ammeter. Then we calculated resistance values to check Ohm's law. We found that the 100 ohm resistor had a resistance of 102.5 ohms, and the 47 ohm resistor had a resistance of 48.5 ohms, which is slightly higher than the labeled value. Then we did an RC circuit. The setup was 1 battery, 1 bulb, that was 10 ohms, and 1 capacitor. We first charged the capacitor by connecting the battery and observing bulb brightness over time. Then we discharged by disconnecting the battery and connecting the capacitor to the bulb. We observed bulb brightness over time. And we repeated this with a 20 ohm bulb and recorded charging and discharging times. The charging and discharging times with the 10 ohm bulb was 11.81 seconds and 14.95 seconds respectively. For the 20 ohm bulb, the charging time was 12.27 seconds and the discharging time was 19.73 seconds. So ultimately we found that the higher resistance bulb results in significantly longer discharging time. Some sources of error that could account for the data discrepancies between the predicted and actual values are miscalibrated voltmeters and ammeters, improperly built circuits, old worn-down components, and a delayed reaction time when recording times. For the additional questions, the first question was, what if you charge a capacitor with no resistor? How quickly would it charge, and would this prediction happen in real life? The ideal model predicts that the capacitor will reach full charge instantaneously. However, this is an ideal model, and in real life, there may be confounding variables that delay the charge. The second question was use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery. Why is the measured time different from the predicted time? The predicted time is based on an ideal scenario where no confounding variables exist. So it's possible that there are environmental factors that introduce resistance to the circuit when the prediction model expects none. Thank you for listening.